We continue to learn Chapter 5, Orthogonality. Section 3, Least Squares Problems. Part 2, Examples. Example 1, find the least square solution to the system. The system is a 3×2 system. So we first write the normal equation. So it's A transpose times A times X equals A transpose times B, where A is a coefficient matrix of this linear system, and B is a right-hand side vector. So after you have this normal equation, you can solve its solution x1, x2. The values are here. So this is a least square solution. If the relationship between the variables is actually linear and the data involves slight error, it would be disastrous to use an interpolating polynomial. We can see from this figure. Okay, so here we have some data points here, and if you use interpolating polynomial, you may get such function, which is far from the true one in the red line here. Okay. Now, given a table of data, here we have x m points, x1, x2 till xm, and we have y is observed value as y1, y2 till ym. We wish to find a linear function y equals c0 plus c1x that best fits the data in the least square sense. If we require that yi equals c0 plus c1xi for I varies from 1 to m, because we have many m here, so from here you will get, in fact, overdetermined linear system. In general, there's no solution for this linear system. However, you can try to find a least square solution to this overdetermined system. So let's see. We can get a system of m equations in two unknowns. So what we want to determine is the coefficients of the linear function, c0, c1. Okay, and we have this one, c0 plus c1x1 equals y1, and the second row, c0 plus c1x2 equals y2, and the last row is c0 plus c1xm equals ym. The best least squares fit to the data by a linear function, you can just solve the least square solution to this linear system. So in fact, you will solve about this matrix is transpose times this matrix times c0, c1 equals the transpose matrix of the coefficient matrix times the right-hand side vector y. Let's see this example. Given the data here, x, you have 3 points, 0, 3, 6. And y value, you have 3 values corresponding to the x value, you have 1, 4, 5. Ask you to find the best least squares fit by a linear function. So its solution is just like here. We try to solve AC equals y, where A, the first column are all 1, 1, 1. Right? Entries are all 1, 1, 1. The second column comes from here, the x value, 0, 3, 6. And C, these unknown coefficients, C0, C1, what you want to know is coefficients for the linear function. And Y, the right-hand side vector, is 1, 4, 5. So the normal equations A transpose A times C equals A transpose Y can be simplified to this linear system. You compute A transpose A is here, and you compute A transpose Y here, 10, 42. And then you can solve this C0, C1, find these coefficients. Thus, the best linear least squares fit is given by Y equals 4 over 3, C0 plus C1, 2 over 3 times X. Also, sometimes maybe linear function is not a good candidate. So we would use a higher degree polynomial. To find the coefficients C0, C1 till Cn of the best least squares fit to this data, you have x, x1, x2 till xm. You have after the function operates on those variables, you will have observed data y1, y2 till yn. By a polynomial of degree n, we must find the best least square solution to this system. See, the first column, the entries are all ones. The second column is x1, x2 till xm. The third column, the entries are x1 power 2, x2 power 2 till xm power 2. And the last column is x1 power n, x2 power n till xm power n. And what you want to know are the coefficients here, C0, C1 till Cn. And the right-hand side vector are the m observed data. So y1, y2 till ym. So for example, the first row means that C0 plus C1x1 plus till plus Cnx1 power n equals y1. We try to find such coefficients here, satisfy this equation. And for the m data points, we want to find these m equations hold. For example, example 3, find the best quadratic least squares fit to the data. So be careful, here is a quadratic least squares fit. It's not linear least squares fit. So we need to use a quadratic function to approximate, to find the best one that represents the data, right? The function, the operation on this data. For this example, the system becomes here. Okay, the first column is 1, 1, 1, 1. The second column is x1, x2, x3, x4. So it's 0, 1, 2, 3. The third column is power 2. So it's 0, 1, 4, 9. And because it's quadratic function, we only consider 3 columns. Okay, so it's C0, C1, C2. And the right hand side is y. So it's 3, 2, 4, 4. So the quadratic function should be y equals C0 plus C1x plus C2x power 2. Okay, and this is an overdetermined system. So we seek the least square solution. So we try to find its normal equation. Coefficient matrix transpose times this one equals the transpose of the coefficient matrix times the right-hand side vector. Right? So this is the normal equations. Then you solve this linear system and you find the unknowns C0, C1, C2. And then the best quadratic least squares fit should be this polynomial, quadratic polynomial, or quadratic function. P of x equals C0 2.75 minus 0.25 times x, so here is C1, plus C2 times x power 2, C2 is 0.25. So we get its best quadratic least squares fit.